This is an intuitive discussion of the multiplicative nature of Euler's phi function for semiprime integers. For any given positive integer k, the phi function outputs the number of integers less than or equal to k that do not share any common factors other than 1 with k. So for example, the phi of 9 is 6, because there are 6 numbers less than or equal to 9 that don't share any common factors other than 1 with 9. On the other hand, 3, 6, and 9 do share common factors with 9. 3 shares a factor of 3 with 9, 6 shares a factor of 3 with 9, and 9 shares a factor of 3 and 9 with 9. So it follows that there must be 6 remaining numbers that don't share common factors other than 1 with 9. Therefore, the phi of 9 is 6. In the RSA encryption cryptosystem, Euler's phi function computes the phi of the semiprime number n, which is the product of two very large prime numbers p and q. The phi of that semiprime n is denoted phi n, and is then used as an upper bound value to select an appropriate value for the encryption key E. And both phi n and E are subsequently used to compute a value of the decryption key D in the equation E times D mod phi n is equal to 1. When a key generator is in the process of generating the public and private values for an RSA encryption scheme, he or she will compute the phi of n in the following manner. Phi of n is equal to p minus 1 times q minus 1. Or in other words, the phi of n is equal to the phi of p times the phi of q, where p and q again are those two sole non-trivial factors of n. So the fact that the phi of some semiprime number n can be computed as the product of the phis of its constituent factors means that the phi function is multiplicative for semiprime numbers. So what I'm hoping to do today is provide an intuitive understanding of why the phi of n can be computed in such a way. In other words, why is Euler's phi function multiplicative for semiprime numbers? So starting with something a little simpler first. It's fact that the phi of some prime number p is equivalent to p minus 1. If you're particularly familiar with Euler's phi function, you can probably see why this is pretty quickly. A prime number, by definition, is a number that has no factors other than itself and 1. The phi function, in turn, outputs how many numbers are less than or equal to a given number that don't share any common factors other than 1 with that number. So, for a prime number p, which only has one factor less than or equal to itself that it shares a common factor other than 1 with, namely itself, it easily follows that the phi of any prime number p will be p minus 1, because p only has p as a number that it shares a common factor other than 1 with. For example, if I'm computing the phi of the prime number 7, I know that there is only one number less than or equal to 7 that shares a common factor other than 1 with 7. That's just 7 itself. That leaves me with 6 other numbers less than or equal to 7 that don't share any common factors other than 1 with 7. Therefore, the phi of 7 is 6, or 7 minus 1. Okay, so you hopefully see why the phi of a prime number is just 1 less than the prime number itself. So now, given some semi-prime number n that we know is the result of the multiplication of two prime numbers p and q, let's now talk about why the phi of that semiprime number n is equal to p minus 1 times q minus 1, which we now know is just phi of p times phi of q. Okay, so let's say that I've got this semiprime number 143, which is the product of the two prime numbers 11 and 13. So let's just manually go through and list multiples of 11 and 13 up until and including 143. Okay, so for 11 I have 11, 22, 33, 44, so on until I reach 143, or 11 times 13. For 13 I similarly have 13, 26, 39, so on until I again reach 143, or 13 times 11. So these numbers are the only numbers less than or equal to 143 that will share common factors other than 1 with 143, because it is only multiples of 143's two prime number factors, 11 and 13, that will share common factors with 143, because it is only multiples of those two prime numbers that will ever be products of integers involving the prime numbers themselves. Okay, so how many multiples of 11 do I have? 13, because 11 times 13 equals 143. And how many multiples of 13 do I have? 11, because 13 times 11 equals 143. So how many total numbers do I have? Well, if we're calling P 11 and Q 13, then I have P plus Q numbers up here, or 24 numbers. But I've got 143 up here twice, so I'm going to cross one of them out so that I don't double count it. So now I have P plus Q minus 1 numbers up here, or 23 numbers. So I have P plus Q minus 1 numbers that are less than or equal to 143 that share common factors other than 1 with 143. So that means that if 143 is equal to P times Q, I have P times Q minus the quantity P plus Q minus 1 numbers that are less than or equal to 143 that do not share common factors other than 1 with 143. Or, sticking with our example, I have 143 minus 23, or 120, numbers that don't share common factors other than 1 with 143. Okay, so now up here in the top left-hand corner, I've defined the phi of n as p minus 1 times q minus 1. And if I multiply that out, I get pq minus p minus q plus 1, or pq minus the entire quantity p plus q minus 1. And this is precisely equivalent to what I found down here. And if I want to convince myself even further, I can plug in p and q into p minus 1 times q minus 1, or 11 minus 1 times 13 minus 1, and end up with 10 times 12, which is of course equivalent to 120, which again is precisely what we found down here. And that, in a nutshell, is intuitively why the phi of a semiprime number is multiplicative, why we can say that the phi of the semiprime n is equal to the product of the phi of its two constituent factors. As always, I hope this was helpful. Thank you for listening, and stay safe.